I'd like to introduce Dr. Scott Shearer, who's John's boss and also his PhD lead professor. Scott has his PhD, master's, and undergraduate work from Ohio State. Following that, he went off to Kentucky and worked in the biological engineering department there, and has since returned as chair of the biological, I got to make sure I get it right, Scott, chair of food, agriculture, and biological engineering at Ohio State University. He's been in academia for 28 years now, studying this whole aspect of the machine relationship to the soil and to the productivity. And so although I've asked him to concentrate on compaction as a function of today's event, what this group really is doing is advancing precision ag in Ohio and throughout the U.S. and North America. But it all relates back to how they see how the equipment has become tougher and tougher to relate to the soil. So without further ado, Scott Shearer.
Thank you for the introduction, Ian. One of the things that we look at when we look at the machinery-soil interface, and I think most of you are going to recognize this pretty quickly, gross vehicle weights have increased substantially. I use this plot, and I'll explain it a little bit. These are tractors that were tested at the University of Nebraska. And on the vertical axis is the ballasted tractor mass of that tractor being tested. Along the x-axis is the year the tractors were tested, and that goes from about 1920 up to 2010. The thing I want to point out is between 1920 and about 1960 is we had modest growth in tractor size. Okay? What happened in 1960, though, that caused things to kind of take off and the slope of the curve in terms of the rate of tractor growth to grow substantially? The advent of the diesel engine. Okay? So it's been kind of an interesting time, but the point that I want to make is if we look at the slope of the green line, again, those are the biggest tractors being built, we've seen an average increase in the ballasted tractor mass of the largest tractor produced increased by 900 pounds per year, sustained now for 50 years. Pretty interesting in some respects. Now, I realize that a lot of people use smaller equipment, and I realize that some of the used equipment is going to turn over as well, but I see really nothing stopping the trend towards higher horsepower tractors. The point that I want to make is, as we see this bigger equipment, especially higher horsepower tractors, you have to have about 120 pounds of tractor weight, ballasted tractor weight, to take advantage of each engine horsepower if you're taking power out through the drawbar. Okay? So necessarily as engine horsepower goes up, so does gross vehicle weight. And I think we're paying a significant penalty in some respects in terms of soil quality and the compaction factor. I'm not picking on manufacturers. Please don't misunderstand me when I show this. But you realize last year that AGCO introduced a 500-horse fixed frame tractor. Now, Fendt, it's being built by Fendt, okay? But they've also introduced it in North America under the Challenger badge. And you see the European version on the left and kind of the U.S. version or the North American version on the right in some respects. But did you ever dream you'd see a 500-horse row crop, fixed frame tractor in your lifetime? I know that I never envisioned that when I kind of got started in agriculture. I'm also wondering who needs a 500-horse row crop, fixed frame tractor. Well, we discovered that, and I'm going to show you a little bit towards the end of the presentation why we might need that horsepower now. I show this only because, and we know that there's not a lot of these DB120s that have been sold, but my point still remains in some respects that higher horsepower means your implements get bigger. One of the governing things in terms of pulling this planter, though, is not necessarily the operation in the field. It's the size of the tractor required to move it up and down public thoroughfares. So when you fold that planter up and you look at the hitch load on it, you need a minimum size tractor to handle the hitch load as you're moving from field to field. And that really governs the size of the tractor more so than necessarily engine horsepower required to pull the planter. Grain carts aren't getting any smaller, are they? Andrew's going to come up and talk in a little bit, but Andrew likes kind of pushing things to the limit. This is a 1,300 bushel grain cart, and Andrew was really proud. He said, you know, you can get 1,400 bushels on that. Okay. Andrew also was able to take a Class 7 combine and harvest 5,600 bushels an hour. Okay. And I said, Andrew, how'd you do that? And he goes, we just got to drive faster. And I said, Andrew, how fast were you going? He goes, 7.5 miles an hour. You imagine harvesting corn at 7.5 miles an hour? Kind of getting back to the grain cart situation, one of the things with telematics is we're able to track where this equipment's been in the field now. And we're going to have a person on the program a little bit later talking about controlled traffic, but when I look at this field, I don't necessarily think the farmer was practicing controlled traffic, okay? And in fact, all of the grain came out down the bottom or the center of the field where you see the little flag, if you will. And the front of that, or the center of that field got trafficked pretty heavily at harvest time. Now, the year that this was trafficked, as I recall, it wasn't too bad a year at the harvest time anyways in terms of soil moisture, but imagine that occurring during a wet year and think about the long-term damage. My agenda, and I'm going to apologize, but I'm going to kind of go back to some of the fundamentals that we know. I'm going to tell you as much as anything, compaction, at least the study of it, there's two kind of approaches. There's kind of a theoretical approach that sometimes the theory doesn't hold up very well, and then there's this kind of field scale research approach, and sometimes the results there aren't very easily replicated. But I think when you put the two of those together, it kind of tells a story about some of the events that cause compaction and some of the impacts and the lasting impacts of those compaction events. So I'm going to talk a little bit about tires and tracks in terms of traction versus transport, okay? We put vehicles on wheels for two reasons, or vehicles on tracks for two reasons. We're either going to basically transmit power to the ground, or we're going to use that vehicle to traverse the field. I'm going to talk about contact and internal soil pressures, and I think that's an important point. But I'm going to do that from two perspectives. I'm going to look at Sohny, which was a German engineer who back in 1957 kind of set the course in terms of a lot of the things that we use today to describe what's going on in the field. And then Rethmel and Harris were two engineers at Firestone that kind of updated this soil pressure issue and how to go about that. Talk a little bit about traction mechanics because I think we need to do that. Again, you got high horsepower equipment, you have to have mass or you have to have weight or it's not effective. Talk a little bit about proper ballasting. Then I'm going to get into yield loss estimation, a couple different methods there, and then talk about some recent developments. After I get done and after break, then Andrew's going to come up and talk a lot about our field research and put some numbers with some of the things we're talking about in terms of what happens as a result of the compaction event. So traction versus transport. We look at a traction or a transport device. We can really break them into two categories. There's tracks and there's tires, and we can talk about whether or not you need to be using tires or tracks, and we'll try to get to that. But basically, these devices are going to provide vertical support. It's also going to allow you to transmit power to the ground, okay? One of the things that we know when we transmit power to the ground is soil fails in shear, okay? And I'm going to come back to this time and time again. But when soil fails in shear, it means in order to transmit power through the tire to the ground, it's going to come out through the drawbar, you have to have wheel slip or you have to have track slip in order for that to be effective or efficient. And that's kind of counter to what a lot of people think in some respects. This transport device, in some respects, you're going to have an unpowered wheel, and now it's all about flotation and being able to basically support that load across the field. And obviously, we want to do that without making ruts in the field, but we're also concerned about that surface compaction versus deep compaction as well. So just a kind of a diagram. And what we have to be thinking about is, in the case of a tire rolling across the soil surface, there's two things that's happening. First of all, the tire deforms, and that's very important. But the other thing is the soil also deforms in response to that tire, okay? Both of these things go together to create rolling resistance. So we have to put enough power into the wheel to get it to move across the field in some respects. But depending upon the loading on that wheel and how much power we're putting into it, we can have dramatically different effects in some respects. I'm going to go back to the Sohny work, and you've seen this replicated in a number of locations, but going back to this paper that was presented in 1957 really is the defining work. This person really looked at contact pressures, and there were some mathematical formulas for it, and so basically what we're showing here is the difference in load intensity. And you can kind of think of it as a point load, but a point load over a small area. And it shows the pressure that develops in the soil below the soil surface and the response to that, okay? And so as you go across, these intensity factors get a little bit higher in some respects. And so the only reason why I want to show these is it kind of sets the stage for how we're going to look at some of these soil stresses or soil pressures, if you will, in various conditions. So here's one where we have different loadings, and basically what they're trying to do is maintain the soil contact pressure or the tire pressure, which really end up being about the same, but the load increases. And so on the left-hand side, you got 660 pounds. On the right-hand side, you got 2,200. But that contact pressure, if you will, is the same for all those wheels. The important thing to look at is the cone of influence or the depth of influence of what happens to the soil pressure below that tire load. And as you go to the right, notice it goes deeper and deeper. You remember John talking about axle load being the thing that governs deep compaction? This is the reason why, if you will, axle load governs deep compaction, okay? Doesn't necessarily have everything to do with the contact pressure. Contact pressure is important for surface compaction, but that deep compaction is going to be a function of gross vehicle weight or gross axle load, okay? And that's one of the take-home messages out of this person's work. In this case now, one of the things we're looking at as we go across from left to right is the soil moisture content. And on the left-hand side, you have a hard, dry soil. And the tire doesn't deform much or the soil doesn't deform much, and so you don't have much contact area. However, as we go to the right now, notice the soil gets wetter and we have more contact area between the tire and the soil because the soil, well, and in some cases the tire is deforming. But most importantly, notice the depressions or the depth of the wheel track left as you go into wetter soils. And so again, John was saying you don't want to traffic wet soils. That's one of the things you want to try to avoid. Now, having said that, we realize at harvest time, you got a window to get the crop out of the field, and so some people are going to traffic that field anyways. So how do we minimize some of the problems? John talked a little bit about the fact that on the first pass, you do about 80% of the damage. And you can kind of think of that, when I make that first pass, my rut, I'm going to get 80% of the depression. On subsequent passes, there's still some damage, but it's not quite as much. So really, in some respects, it argues for if you're going to take loads out of a field, mess up one part of your field and try not to mess up the other part. But again, this could be part of the reason that we see controlled traffic being such an advantage in some respects. Okay, we're going to disturb a defined amount of soil. We're going to accept that, and then we're going to try to leave the remainder of the field untrafficked. Okay. This one here is, I think, very important from the perspective of looking at, we have a hard, dry soil with normal density, and then a wet soil, but these are basically the same load across there, the same tire pressure. And again, the tire sinks a little bit deeper, but as you get over to the other side, don't forget the cone of influence or the depth into the soil that we're seeing that compaction event increases. And so dry soil will support very high gross vehicle weights with minor or moderate disturbance to the soil, minor damage in the way of compaction. You get into wet soils, and that's really when the problems get amplified. Everybody starts talking about the area of contact, okay? And so as we look from left to right here in some respects, the tire surface area is increasing. We can run the tires at lower pressures. You have to think about the size of the tire and the inflation pressure. But really notice what's happening on the left-hand side. We have a high-pressure tire, 40 PSI, but it's a smaller tire. You need the 40 PSI to support the load. Look at the depth of influence into the soil. So what this one really tells me in some respects is we want to have the appropriate size tires so that we can run the lower inflation pressures, reduce the contact pressures, if you will. But if we can do that, anything that indicates to me that we can lower the pressure in the tires would be a good thing in terms of compaction. And again, it reduces that amount of influence and that depth of influence in terms of the compaction event. So what do we learn from this? Contact area between tire and soil is a function of soil moisture, and don't traffic wet soils. Contact area, tire size and number affect the quantity of displaced soil. More tire contact is better in some respects, most cases. Majority of compaction is accomplished in the first pass. Multiple passes, not necessarily additive effect. There is an increase in effect, but it's not directly additive. Surface contact pressures very close to the tire inflation pressure. So if you're running your tires at about 12 psi, my guess is the contact pressure at the soil surface is going to be pretty close to that. And that's not a hard, steadfast rule, but it's pretty close. What you want to do is run your tires at the lowest allowable pressure. I caution people, as you let the air out of the tires, though, don't void the tire manufacturer's warranty, okay? And so they have those load inflation pressure tables generally, and you got to make certain when you're reducing the air pressure in your tires when you're going off-road that you do it such that you've not voided the warranty, okay? Another comment to make, too, is most agricultural tires are designed to be run at about 5 miles an hour. And if you begin running them at lower speeds and you're still putting a lot of power through them, you can get into some trouble, too, in terms of the warranty. So just a couple notes there. Depth of compaction influence is a function of tire load, not tire pressure necessarily. Reduce axle loads to reduce compaction, okay? Sometimes you can do that, sometimes you can't. But what it argues for in some respects is if I'm going to buy a grain cart, and I need a big grain cart, maybe I want multiple axles under it instead of a single axle, okay? So just thinking about that. Multiple axles, better option than multiple tires on fewer axles. You know, the question is, I'm going to run duals or triples, okay? Well, if I can run more axles, and there's some concept tractors out of Europe, that makes sense. So most of our tractors are 2 axles. We see some concept tractors out of Europe where we actually see some 3-axle tractors, okay? Multiple or wider tires, better option for high axle loads, given the fact that you can't increase the number of axles. So I want to switch gears a little bit now and talk about Rethmel and Harris, because they began doing some very interesting work, and these are the Firestone engineers out of Northeast Ohio looking at soil pressures. Now, there's some problems with what they've been doing, and I'll come to that at the end, but I think it's kind of interesting work nonetheless. They came up with this mat by TechScan that they could place below the soil surface. And this had literally thousands of sensing elements in it. If I'm not mistaken, they put 4 of those mats in. There were about 16,000 sensing elements. And think of them as digital scales or pressure transducers. But what they were able to do is generate an image as the tractor was driven over that mat. Okay? Now, what they would do is construct sand pits and other places where they would place this mat at different depths in the soil, okay? So again, kind of interesting work. So here's one of their test situations, and that happens to be a sand pit that the tractor is going to drive over, but that mat is buried below that soil surface, and in this case, sand surface. This is a bigger sand pit they did because they wanted to try some bigger tractors. They also wanted to look at the time duration of things, okay? So these are some of the images that they got out of this, and please understand that the colors in there represent the contact pressures. Upper left-hand corner is basically a tire pressure, 29 psi, but it's 2 inches below the sand surface, if you will. The one on the upper right is 4 inches below. The one on the lower left, 6 inches below, and then the one on the lower right, 8 inches below, okay? Now, on that top one, you see the tractor tire lugs very clearly, and that makes sense, okay? And in fact, those red areas in the lugs, those are going to be very high contact pressures. Now, as you get below the soil surface, though, you kind of get a diffusion, if you will, of those contact stresses in some respects, and you end up getting bigger kind of area distributions in terms of pressure, okay? So the next thing they did is they said, well, let's run a tractor over it, okay? So on the left-hand side is the pressure response essentially for the entire event. So they ran that tractor over. You got the front idler, you got the middle idlers, and then you got the big drive wheel in the rear. So they kind of had 5 different points to it in terms of where the idlers and the front and rear wheel drives are running over it. But the very one on the left is actually the composite. Okay, so we see the combined effect in terms of pressures that mat experienced. Okay, well, interesting, okay, but still, how does that tell us how we ought to be managing? Should we be buying tires? Should we be buying tracks? What should we be doing? Now, a comment here. Firestone, basically when this work was being done, was a tire manufacturer. And one of the things that was happening is they were losing out to a number of the companies that were coming out with tracks, okay? So on the other hand, now we have this new tire technology, IF, okay? And basically it allows the sidewalls to flex. We also have VF tires that allow the sidewalls really to flex. So let's not forget where Firestone was at. By the way, Firestone is in the tracks business now too, as I understand. So they were looking at wheeled tractors versus track tractors, and they were also looking at IF tires. So this is kind of interesting. They did this multiple passes. So you got standard tires at the left. And if you look there, we see some pretty significant areas. We see some pretty high contact pressures. You have IF tires in the middle, okay? And then you have tracks on the right-hand side. So does this really tell us anything yet? Well, it's getting a little bit closer in some respects. But when I look at those images, the only thing I really notice is the IF tires are probably better than the standard tires. I don't know whether there's enough information to make any decision about the tracks versus the IF or tracks versus standard tires, because you got bigger contact area for the standard and IF tires because they're running duals, okay? So now we get to this one, it gets a little bit more interesting, okay? Standard tires on the left-hand side, and then you got the IF tires, and then you have tracks. Well, notice what happened in this case. By the way, this is at 7 inches. The other one was at 3 inches, so different depths. But you look at the IF tires, and essentially, at least for the thresholds they were using to create these images, essentially the IF tires had little effect at 7 inches of depth. The tracks, a reduced effect at 7 inches of depth, but if you look over on the left-hand side with standard tires, still a pretty substantial influence, okay? So again, I think this begins telling us something, but there's a couple fallacies here that are very important to understand. First off, they were doing this in a sand pit. Sand may not be very representative of what would happen in a clay or a loam soil. And so that's the first thing to understand. The second thing is, while they had their tractors ballasted for field conditions, there was no load on the drawbar, okay? When you load the drawbar, let's not forget it's changing the downforce on the wheels as you would pass over the soil surface. And so two things there that are kind of important to understand. On the other hand, that tech scan mat, I think, was $60,000 or $70,000, and I don't think they really wanted to destroy it every time they drove over it. So an interesting time, okay? But we have some technology that allows us today to look at things a little bit differently. So based on testing conducted, it was determined standard dual tires create more subsurface pressure compared with, that should be 18-inch tracks, not 1-inch tracks, okay? Operating tires at IF conditions offer an advantage in subsurface pressures, and I think that was pretty clear here. And then I note there additional testing is required for traction devices for high draft loads, and we've been talking to them about how we might do that. We're trying to partner with them. The other thing is additional testing required to determine what level of subsurface pressures correlate to measurable crop impact. So it's nice we have those pressures, but really, how's that translate into reduced yield? And so something that's very important. So kind of gone through that contact stress area, looking at what's happening with the area, the surface area of the tire, the soil interface, and some of those things. Now let's talk a little bit about traction mechanics, because one of the things that's important is, can you transmit the power to the soil, okay? And again, one of the things I told you before is we need about, at least for a mechanical front wheel assist tractor, somewhere around 120 pounds of tractor weight for each engine horsepower to take advantage of the horsepower, okay? This next part really comes out of a lot of work that was done by John Deere, and it was done originally in a soil bin with bicycle tires, okay? Now, how applicable is that to farming? Well, most of you would say not very applicable, but they've gone well beyond that now, several of the engineers, and they're able to use this empirical model to do a very good job of predicting tractive efficiency for actually wheeled and track tractors, okay? So a lot of this empirical model got to develop back in the 1960s, but has been refined continuously about every 10 to 15 years since then by engineers at John Deere. And so I give John Deere a lot of credit for understanding that tractive efficiency. But the biggest thing is we put so much torque into the wheel or the axle, or we put so much torque into the drive wheel on the tracks, what are we able to take out in terms of draft force at the drawbar? And that's really one of the biggest things we need to talk about here. We always talk about properly ballasting a tractor. What's that really mean? How do we know when we have it ballasted correctly? Okay? And the one other note in here, although we're going to be talking about wheels almost exclusively, the same approach applies to tracks. Okay? And so let's not forget that in some respects. I'm not going to attempt to explain all this diagram. The biggest thing that I want you to understand is if we look in the upper right-hand part of that diagram, the biggest thing that I want you to note is the x-axis going horizontally, that's wheel slip. And that's in, it's a decimal form here, but 0.5 would be 50% wheel slip, okay? When you get to 1, that's 100% wheel slip, so that means the tractor, while the pole might be maximum, isn't going anywhere, okay? And, oh, by the way, if you're at 50% wheel slip, you're only going about half as fast as you think you are, okay? But the point that I want to make here is please notice that pole increases with slip, okay? Does this explain why when you go to a tractor pole, you see the tires turning at a very high speed, maybe 80, 90 miles an hour for some of the high-end pullers, but yet the tractor is going how fast? Okay? You kind of get into a friction pulling, but what they're trying to do is get that maximum force on the sled. Now, we're not going to do that in a field, are we? Okay? But just try to understand that as you increase that pull and you're trying to put that power through the tire, necessarily there's going to be wheel slip. And that's one of the takeaway messages out of here. This one becomes a very interesting diagram, and there's a lot of curves on there, but I want to focus on one, and that's tractive efficiency ratio, okay? So think of tractive efficiency as we put so much power into the transmission, and we get so much out at the drawbar, okay? So how much do we get out the drawbar versus what we put in? Well, if you look at that blue curve, it maxes out at what, about 75%? So that traction process is inefficient. We lose about 25% of the power. But you'll also notice that tractive efficiency, depending upon what the wheel slip is, we can waste a lot of fuel, okay? So if we have the tractor ballasted such we don't have any wheel slip, we could be down there with a tractive efficiency of 40%, which means we're wasting a tremendous amount of fuel in the field. On the other hand, if we get on the other side of that in some respects, okay, and while the wheel slip goes up, you'll notice that we can also get to that point where we're transferring maximum power. If we go too far beyond that, though, we start going down again. And so really, when I look at that chart, the tractive efficiency ratio kind of peaks out at about 0.7, but somewhere around about 10% slip, okay? So what this is telling me is in order to get maximum energy transfer through the wheels or tracks, in this case the wheels, I need to ballast my tractor so I have it about 10% wheel slip. Okay, if I don't do that, I'm sacrificing fuel. And, you know, maybe it's a little less expensive today than it was a few years back, but my guess is still it's a pretty significant part of your overall operating cost. This is that same diagram, but it's kind of recast a little bit. And the reason why they recast it is because we're going to talk about a couple other things here in terms of tracks versus tires, okay? So we got tractive efficiency in the blue on top. And you'll notice that if we maximize tractive efficiency at about 70%, we'll go down to the green curve, and the green curve is actually slip, okay? Now, I know it's kind of hard to visualize and understand, but when I go to the next one, it kind of tells you whether or not you ought to be using tracks or tires when you're simply talking about tractive efficiency, okay? So we go to the next one. This one is PSI, pressure in the tire. The important thing to note here is the red curve is for a 6 psi load on a tire where the tire is inflated to 6 psi. Okay, so we look at the load tables and we know how much ballast weight we have on the tractor. The blue curve is a 6 psi load with a 28 psi tire inflation pressure. Okay, the point that I want to make here is notice the difference in the tractive efficiency. If I inflate that tire to 28 psi, I max out somewhere, what, about 66, 67%. If I drop that pressure as much as I can in the tire, I actually improve my tractive efficiency, and I can get up to about 0.7 or 0.71. Okay? Now, that's counter to a lot of people's intuition. I let air out of my tires, and I'm going to have better fuel efficiency. Okay? But let's go back and think about why that's occurring. When I let air out of the tire, what happens to the sidewall of the tire? it bulges out, right? Well, what happens is when that sidewall bulges out, the contact area for the tire gets greater, okay? And because we have a greater contact area, because soil fails in shear, we get better tractive efficiency, okay? Well, let's take that one step further. What happens if I buy tracks or a tractor with tracks versus tires? Well, the one in the brown is a wheeled tractor, 20.8 R42 duals. The other three are rubber tracked or track tractors, okay? Please notice what's happening to that tractive efficiency. For the wheeled tractor, it maxes out at about 0.72, 0.73. Please note for the red belts, I could be up as high as 0.85, 0.86, okay? This translates into fuel savings, okay? So if I'm sitting here telling you whether or not to buy tracks or tires, one of the things you're going to need to consider is that track going to be on a tractor that I'm trying to take power out of the track, okay? Because then I'm going towards this thing, attractive efficiency, and it goes to my fuel rate. Now, on the other hand, if you're a no-till farmer and you don't have high draft loads, maybe I don't need tracks for high tractive efficiency because I'm not pulling big draft loads, okay? So you got to kind of think about your application. And again, this is going towards tracks or tires. Which one do I buy in some respects, okay? But at least here what I'm beginning to show you is the proof in some respects as to why tracks are a little bit more efficient. Again, it's power in versus power out. And I want to get as much power out of the tractor as I can at the drawbar when I put that into the axle or the tracks that are being driven. Now, we also recognize that tractive efficiency varies depending upon soil texture, okay? We look at concrete there, okay? Now, if I was testing tractors at the University of Nebraska, I'm going to probably get maximum power coming out of the drawbar somewhere around 5, 6, 7% wheel slip. But if I go to a firm soil, that's going to go to about 10%. If I go to a tilled soil, it could go to 12 or 13%. And then if I go to a soft or sandy soil, it could be as high as a 20% wheel slip to maximize tractive efficiency, okay? So soil texture, if you will, or soil type does influence this overall tractive efficiency thing as well. Now, not trying to confuse you, I'm just trying to get you to understand you need slip to maximize or optimize, if you will, not maximize, optimize your fuel consumption. If you want the lowest fuel bill, you need to have the right slip in your driving components. So tracks are more efficient than wheels in terms of this tractive efficiency thing. Optimal tractive efficiency occurs about 10 to 15% slip for wheels and about 4 to 10% slip for tracks. Now, that's part of the difference in the efficiency is you get higher tractive efficiency at a lower slip, okay? Tractive efficiency is a function of soil type as well. So I guess enough for some of the technical stuff. Let's go back and talk a little bit about things such as ballasting, okay? I think we're kind of past this now. Used to be a big discussion about radial versus bias ply tires, okay? And the biggest difference between the two is, and the way you need to think of it is, the sidewalls in a radial tire are different from the tread or the track portion of the tire. And when you look at the construction, you actually, those belts that go around there for the tread or tracks to kind of give the tire stiffness where the lug is different from the radial belts that go from bead to bead on the tire. When you look at the bias ply, though, the tread and the sidewall of the tire was all wrapped into one, okay? What this means is the radial tire, and again, a lot of people look at you like you're nuts. Why are you buying a radial tire for a tractor? It's not like it's going to corner any better. But the main thing is that the sidewall flexes on the tire. And again, it allows the lug portion to flatten out, if you will, and spread out over the soil area, okay? And that's the reason why the radial tires are preferred today over the bias plies. The bias plies are a little more rigid, and so a lot of times you'll get that lug, especially when you inflate the tire, will kind of pop out a little bit, and you don't get quite the soil tire contact with the bias ply tires. The other thing is you cannot run the bias ply tires at a lower inflation pressure either, because obviously you'll compromise the sidewall or ruin the tire. Just some terms in some respects. We talk about section widths of tires. Most of you know and understand that. I can put an 18.4 down between two rows of corn. It's a little bit difficult when I get much beyond that because I start running over corn. Okay, so when I talk about a row crop tire, usually talking about an 18.4, and that's the section width, 18.4 inches. We can talk about the diameter too, but there's also the section height to be concerned about. as much as anything, if we want to increase the contact area between the tire and the soil surface, make the tires wider or make them bigger in diameter. If you notice a lot of our tractors today, especially the high horsepower, one of the only options they have, especially in a row crop case, is to make bigger diameter tires. And we certainly see evidence of that with the higher horsepower tractors today. Nothing magical here, but you have the metric, kind of equivalent of tire ratings. The 520 in this case is the section width in millimeters. The 85% is the aspect ratio, so it's really the section height, the section width. It means the section height of the tire is 85% of the section width. You got the R, which means it's a radial, and then you got the 42, which is a rim diameter in inches, which I don't quite understand why that's metric, but it is what it is, okay? We got the load index, which ends up being a pretty important. You got the speed index, and then you got the tread style. What I want to go back to is most of our radial R1 tires are really designed to be used at 5 miles an hour, okay? And sometimes you get into conditions where the tractor lugs down, you're down around 3 miles an hour, we understand that, but really most of the time you ought to be trying to shoot for that 5 miles an hour to maximize tractor life or tractor tire life. And then there's the old standard sizes too, and those are generally in English units. If there's not a lot of extra in there, it's probably a bi-ply tire. This is kind of, and I'm only going to talk about what's on the right here, but this is kind of indicating what we were talking about in terms of looking at the contact between the tire and the soil surface. The bi-ply tire doesn't have that flex in it quite as much, whereas the radial tire does, so we get a bigger footprint from the radial tire, even though it's the same size, okay? A little bit on the left-hand side is about radial tire construction. I think I described that in the previous slide. So, get to ballasting, okay? For a four-wheel drive tractor, if you look at most operators' manuals, it recommends somewhere between 85 and 125 pounds of tractor mass, tractor weight per engine horsepower, okay? Now, that needs to be distributed between the front and rear axles, okay? One of the things the four-wheel drive tractor manufacturers struggle a lot with is something called power hop. Have any of you experienced power hop on a heavily loaded four-wheel drive tractor? This is when the tractor kind of starts jumping, but if you watch the wheels, they'll actually come off the ground, and instead of going forward, they'll go into a reverse motion, okay? And it's a very destructive process, but what they found is you can manage it by how you ballast the tractor, weight between the front and rear axles, and even tire pressures and some things like that. But for towed implements, they're recommending about 51 to 55% of the weight on the front axle for a four-wheel drive tractor. Historically, they'd always said 60% on the front, 40% on the rear, okay? We know that most of our four-wheel drive tractors are going to be pulling hitched implements that are hitched to the drawbar, if you will, as opposed to being fully integral or semi-integral. We know planters will fall into that category, but you're not quite pulling the same amount of power out of the tractor. So 85 to 125, you know, you kind of split the difference, maybe 110, kind of in the middle somewhere, 110 pounds of tractor mass per engine horsepower, roughly with about 55% of that on the front axle under a static condition. So you drive it on the scales, 55% on the front axle, 45% on the rear. Just about a properly ballasted tractor. The only way to really tell, though, take it out into the field and measure the wheel slip, okay? Once you get an indication of wheel slip, you got a good indication of whether or not your tractor is properly ballasted, okay? And again, in the case of a four-wheel drive tractor, you're trying to hit that probably 10 to 12% area, maybe a little bit above that. Mechanical front-wheel drive tractors, typically 120 to 145 pounds per engine horsepower, a little bit more, okay? Typically, 35 to 40% of that static weight needs to be on the front axle, okay? And again, you're going to go out in the field and you're going to check the slip to see whether or not. Now, the comment that I would make is, if you got a 500 horse tractor and your load is 400 horse, why would you ballast it for 500 horse? Okay, so you want to ballast your tractor for the load in some respects. Again, you also have to look at how the tractor is shipped and your opportunities to add weight to the tractor. Is it going to be wheel weights? Is it going to be suitcase weights on the front? I don't know whether many people are loading tires anymore either, but you know, the practice used to be we put water with calcium chloride in the rear wheels in some respects. So still options there. Then the two-wheel drive tractor, typically the front end can be a little bit lighter, but about the same amount of tractor weight per engine horsepower. So again, you need to observe this because of the fuel efficiency situation. The other thing I'm going to recognize is you use your tractor for multiple field activities. So what I'd be doing is ballasting probably for the high horsepower type loads. But then what we're finding is with some of the pinch row compaction, the tractor's contributing quite a bit to that. And so we see John Deere advocating now that what you want to do is take as much ballast off the tractor during planting conditions as possible. So again, I think we're back into this pattern of trying to manage the weight on the tractor a little bit more rigorously and routinely. Well, yield loss estimation, this is what everybody really cares about. I talked about a lot of the science and the engineering behind that tire soil interface and some of the do's and don'ts in some respects, but really at the end of the day, what's it costing you, okay? And we have a couple things we've been doing at Ohio State, and Andrew's going to come up and talk more in depth about a lot of this, okay? And in great detail in some respects, but really as much as anything, what we've been doing at Ohio State is trying to build on some of that history that I talked about and try to get to that, what's the true cost of compaction, okay? And I'm going to tell you, Andrew has some numbers that will probably get your attention. We can argue whether this is going to be representative of a vast portion of North America or not because it's been done in the state of Ohio, but we are getting to that point where we can put numbers, at least on some of the events that we've been talking about. So, kind of going back to what John talked about and what Andrew's going to talk about in some respects, there's kind of this surface compaction event, which causes some problems. But then there's also this deep compaction going into the subsurface. I'm going to talk about this a little bit more because, again, it's related to gross vehicle weight, okay, and specifically axle load. And that's the most important take-home message. This is some work that came out of, one of my colleagues, Randall Reeder at Ohio State, who's retired now, but he was working with a couple of individuals, I believe, out of Penn State University, and they were trying to characterize really where the yield loss comes from. So if we look at the kind of the small, darker brown triangle, yield loss due to compaction in the topsoil, okay? By the way, that horizontal axis is the number of years that compaction yield reduction is going to be in effect. So if you look there, that surface compaction, we could be losing about 7.5% yield. Then when you look at yield loss due to compaction in the upper part of the subsoil, about another 5 or 6%. But then we notice there's probably going to be about 4% loss to deep compaction. Okay? Now, when we're talking about deep compaction, the question is what constitutes deep compaction? My attitude is if you can mitigate it with tillage, it's probably shallow compaction. Okay? I'm talking about deep compaction that may be down as deep as about 1 meter. And I think that's what's really changed in terms of the tractor size and the equipment size of today. We noticed that high horsepower equipment, the big combines, the big grain carts, I think my personal opinion is it's forcing compaction deeper into the soil. And that's a penalty that we're beginning to pay now that's difficult to mitigate. Now, maybe in some parts of Canada you have some frost lines that go down 3 or 4 feet, and that's great if you do, but in Ohio we don't have that, okay? And frost is one of those things that might kind of even the playing field in some respects. Andrew's going to come up and talk about this. I'm not going to spend a lot of time on it, but Andrew's put together an empirical model to try to predict what the yield loss is, okay? It's a pretty simple model. Andrew's going to simplify it for you. But again, what we're trying to get to is what's the cost? When you make a decision, tires, tracks, IF tires, other types, and operating conditions, what's the concern? This is some data that Randall Reeder had worked on. Again, faculty member at Ohio State, and this is up in Northwest Ohio. And I want to point out a couple things here, and Andrew's going to talk about this more. 10-ton axle loads, on average, there's really no impact. Now, by the way, I don't know that we're getting yield gains necessarily, but again, in Randall Reeder's plots, they traffic the entire surface of the plot, and they notice that. The thing that I think is most important is you go to 20-ton axle loads, and every year there's a yield reduction. I think this is about 10 or 12 years of data. But what I've been telling Randall Reeder is now we got a lot of 30 and 40-ton axle loads. I said, where's your data for that? And think about that. So we're projecting what they might be out at 30 and 40 tons. But again, look at that percentage yield loss when we get to 30 tons if this trend holds up. Okay? Kind of scary in some respects. Here's the one that I think is most important. Randall Reeder had collected some data looking at depth into the soil of influence in terms of compaction events. And so they did it for a 5-ton axle load, probably a 7-ton axle load, 11-ton, and maybe a 17-ton. Okay, but here's this curve. What concerns me is the slope of that curve, that red dashed line, though, going to the right when we get to a 30-ton axle load or a 40-ton, and please note that depth is in inches. So what I'm saying is for some of the axle loads today, we could be seeing compaction as deep as a meter into the soil. It's going to be difficult to mitigate that with tillage, okay? I would also suggest in Northwest Ohio, we might be seeing some evidence in that a lot of our farmers have gone back and split their tile lines, and we have some farmers with tile lines that are on 20 and 30-foot spacings. They're finding it economically advantageous to do that. So it tells me there must be something going on. Now, whether it's compaction or something else, I don't know. But again, it's just one of those things that I would point to that shows some concern. Randall Reeder put this table together, I guess with this, one of his colleagues at the University of Minnesota. But anyways, this was looking at some typical axle loads that are common today. And again, four-wheel drive tractors, slurry tankers, but you get up there, a Class 9 combine, 20-ton axle load, but when you start looking at other things, a 12-row head on a combine, 24-ton axle load, what happens when you go to a 16-row head, okay? Grain carts, those are, I think, the biggest offenders in some respects. Look at that, a 1,200 bushel grain cart between 35 and 40 tons on the axle load. And again, we're trying to project out what damage that is doing in some respects. If it's dry, I'm not quite as concerned about it. If I see that grain cart making lots of wheel tracks when it's loaded, that's when I really start to get concerned. Randall did this work, and what they were doing is kind of look at what happened in the soil below these tractors passing. As much as anything, you kind of got the standard radial tires on top, then you have half tracks, then you have a little bit different, well, I'm sorry, that was singles on the top, then you got duals, the 18.4 R38s, and then you're getting down to some bigger diameter tire sizes and getting into the IF tires and lower inflation pressures, but generally, as you go down in that table, the lower, the bottom of that chart is less of a problem in terms of the effect in terms of compaction. Now, we've got to be careful in terms of the half tracks because I think when this data was done, it may not have been offerings that were necessarily coming from the equipment manufacturers. In other words, they might have been aftermarket type add-on tracks. And so again, you got to kind of go back and look at the size of the tracks. And I just want to give you a feel for what's going on. The IF tires, though, I think there's a lot there in some respects. I'm not going to try to go through this flow chart necessarily, but I think when you look at surface compaction, it manifests itself in different ways, and John talked to that quite a bit, versus subsoil compaction. But the two things that kind of stand out in subsoil compaction is this issue of slowed drainage and this issue of shallower rooting, okay? And I think those two are both very significant from a couple different perspectives, being able to get in and farm the field in some respects, and then also what's going to happen in terms of the crop's response. So yield loss estimation, this is a technique that we're kind of putting together at Ohio State and hopefully kind of gets to my point here. The middle map comes from a yield monitor, okay? On the left-hand side, you'll see an aerial view, and I know it may be kind of difficult to see from the back of the room, but if you look, there are some diagonal lines that look like they're about a 30-degree angle with the horizontal. Those are our compaction plots. Andrew's going to talk a lot about these. But if you look at the remote sensed image, you notice a lot of wheel tracks in the field, and you notice that the crop vigor in those areas was not very good. I go to the yield monitor map, though, I don't see many of those diagonal lines. Because of the nature of yield monitoring, because of the nature of combines, we have a head that could be 8 or 12 rows wide. We're averaging across that. Then it also takes a bit of time for the grain to get from the head up to the top of the clean grain elevator, okay? And so there's a bit of filtering going on with the combine. What we're going back and thinking about doing is using a V12 map, that's a good indication of biomass, to readjust the local distribution of yield monitor data to produce a higher resolution map on the right. John talked about being able to see a lot of these events in the field through the remote sensed imagery. Now what we're trying to do is adjust the yield monitor data to get a handle on what the true cost is to the farmer in terms of compaction, okay? So again, we begin marrying some technologies, and we're going to be able to tell some stories that are pretty significant in the future about what the true cost of soil compaction is going to be. And then we get down to making decisions. Can I afford to buy that IF tire? Okay? Can I afford to switch out? Should I be buying tracks on some of my new equipment? And that's really what we're trying to get to an answer in terms of this trade-off between looking at transport and tractive type situations, gross vehicle weights, and obviously what shows up at the end of the season in terms of the balance coming out of the field. Talk about a few recent developments because I think that's always important. IF tires, basically these sidewalls flex more. You can run them at a lot lower pressures. We're starting to see a lot of these pit demonstrations where they'll layer soil and something that gives a very visible response. This was one that was done by Michelin. And on the right-hand side, you see an IF tire with less soil deformation than the one on the left. Both tires on the same tractor, but they're trying to demonstrate the value of the IF tire. Again, a lot of companies have IF and VF tire technologies, and again, it really is an indication of how much they allow that sidewall to flex under a loaded condition in some respects. And again, inflation pressures are everything in all this. Mitas has this new track tire. I don't know a lot about the technology, but when you begin looking at the tire, it's a bit different than our traditional pneumatic tires. Generally, what we would do is seal between the rim and the tire itself. Obviously, you see this tire is quite a bit different in terms of the tire construction itself. Now, these were supposed to come to market pretty quickly. I don't know whether it's just a European availability right now or not, but it'd be kind of interesting to watch and see what happens with this Mitas tire. But again, if you look at that rear wheel of the tractor, you see quite a bit of deformation out of that tire to kind of spread it out and get that bigger footprint on the ground. Tracks. We got tracks for everything now, don't we? You know, if I go back a few years, there were really only a couple companies kind of in the market producing tracks. Now it seems like, I don't know, every year or so we see another company added. Goodyear got out of the track business. I think they sold out to Continental. Those tracks are produced, I think, in St. Mary's, Ohio. Camoplast, a Canadian company, obviously has quite a bit of the market when you look at especially the high horsepower. Is Camsol another company? I mean, there's a number of them, and I know Firestone's in the track business now, so tracks are really kind of interesting because everybody's thinking about how you put them on all types of equipment. Downsides to tracks, okay? And, you know, everybody talks about the good things. Sometimes they don't talk about the downside. But a lot of times transport speeds over public thoroughfares are going to be limited, okay? We notice, especially on the narrower tracks, a lot of our road speeds on the equipment we've been using are limited to 18 miles an hour. Now, for people that are kind of spread out, that could be a pretty big factor, okay? What it really boils down to in some respects is the width of the track and the loading on that track. In the case of the tracks that we have here from Susi, were put on the John Deere planter. Obviously, you want an 18-inch track to get down between rows of corn. And so there are some issues in terms of being able to road that. We see tracks on sprayers now. One of the other thoughts I have in terms of tracks on sprayers, we begin thinking a lot about high clearance machines for late season N application in corn. I know it's been one of those things that's been a big news item in the U.S. anyways. One of the things I'm thinking about is with putting tracks on some of our existing machines, we could probably increase the ground clearance. And so there could be some added reasons for going to tracks over a wheeled machine in some cases. I was out in Saskatoon and I was marveling at air drills, some of the air seeding equipment, but what is it? Bourgault is building now, I believe, an 1,800 bushel air cart, okay? I'm looking at the size of the four-wheel drive tractor with triples on it, and I'm looking at the size of the product cart, okay? And I've noticed that's rolling over the ground that's already been seeded too, so maybe they need that seed soil contact out there to, I don't know. All I'm saying is we're getting to a point where there's going to be a variety of options for people, and the radial tire certainly, the IF, VF tires, and now tracks are going to be things that people might want to consider. I put this up here, and this was from Firestone. They're getting ready to build a tire, a row crop tire, an 18.4 tire with a rolling circumference index of 52. I know that doesn't mean a lot to a lot of people. I plotted this out though, and that's going to be a tire with an overall outside diameter of over 100 inches. Thanks. Okay? Think about that, a 100-inch diameter row crop tire. Okay? That's what I said. As tractors get higher horsepower, if it's still going to be a row crop tractor, the only option you really have is to go bigger diameter in some respects. And obviously, somebody's getting ready to build a 700-horse row crop tractor. So I'll show you this one because there's other options too. And Andrew has a need for pushing things to the limit. So Andrew's in the tractor driving. Here's Andrew planting. Andrew was in a hurry to get the field done. He's at 13.5 miles an hour. By the way, the yield data didn't show any difference between what was planted at 13.5 and what was planted at 5 miles an hour. Andrew's problem was he ran out of engine horsepower. That was a 400-horse road track or Steiger road track. If he would have had 470, Andrew probably would have been going 15 or 16, okay? That is where we're at with technology today. And so there's really two options. The equipment's going to get bigger, or maybe it's going to get faster. And we're going to reconsider the traction devices depending upon which way we go. At the end of the session today, we'll come back and I'll talk about something else, which is where I think things are going. And the reason why I think they're headed in this other direction is because of the compaction events and what's happening to our soil. So just to kind of wrap this up, for traction, you need to properly ballast the tractor for the anticipated load. I'm going to say about 120 pounds of tractor mass per horsepower for mechanical front wheel assist. You want the lowest possible GVW for the operation. So if you don't have a high horsepower operation, don't put all the weight on the tractor. You need proper weight split between the front, that should be front and rear axles, 40% on the front, 60% on the rear. Depends on the tractor. Four-wheel drive be a little bit different. Tractor efficiency is maximized for wheel slip by tractor type, typically 10 to 20% for wheeled tractors. So you got that slip monitor on the tractor, use it, okay? Adjust ballast if slip is too low or too high. You might need to take a little off. You might need to put a little bit more on, whatever the case may be. Tracks are better than wheels. There's a higher tractive efficiency. You use less fuel, okay? But note, you can buy a lot of fuel for the additional cost of tracks. And so you got to think about what your specific farming operation is and your high draft loads. You want to run the lowest allowable tire pressure, but you got to observe the warranty, okay? Don't run out there and just let all your tire pressures out to 6 PSI, or you might be upset when the tire fails and you're buying a new tire and they won't stand behind it. Make certain you look at the load inflation pressure tables and make certain you're observing the warranty for the tire, okay? What you really want to do, though, is you want to maximize surface contact area so you can reduce the contact pressure and increase fuel efficiency, okay? Radial tire construction is better than bias ply. If we were having this 10, 15 years ago, that would have been a more important statement, but mostly everything is radial tires today, at least the vast majority. Again, the sidewalls flex more. IF and LF tires are great. You may be somewhat limited in some of the options in terms of tire sizes. We know now the manufacturers are beginning to make IF and LF tires for planters. And so again, we're seeing this technology become pretty pervasive. Now, that was for traction. This is for loads on the soil. These are when we're moving loads across the soil. Axle load determines depth of compaction. More axles are better for alleviating compaction. More tires per axle is a less attractive alternative to more axles. Okay, so some people thinking, I go to triples or something like that, that's better. Well, it is better, but I would have rather seen you add another axle, okay, in some respects. Axle loads of 10 tons or less do minimal damage. IF and LF tires, again, are great. Size options may be limited. If you're limited by row crop requirements and 18.4 section width, the only option may be to go to bigger diameter tires, okay? Tracks are typically better than row crop tires, okay? I think comparing it to a radial tire, not necessarily an IF or an LF. Wide tracks are better than narrow, but again, are you being forced to operate in a row crop type application? High inflation pressures lead to more serious compaction events. We want to try to reduce that inflation pressure as much as we can within the manufacturer's recommendations. Limit field activities in wet soils. Sometimes you can do that. Sometimes you're going to be forced to go on marginal conditions. We understand that. But again, when you can make that decision, hold back. Soil movement. Basically, when you see soil movement, you know you're doing damage. And so to the extent you can minimize those types of events, you'll really help yourself in terms of compaction. So with that, I think I'm done. Thank you very much.